cs407 Numerical Analysis, Section 5.3 Simpson's Rule and Newton-Cotes rules. We'll begin our lecture with a review of how to derive the basic trapezoid rule. So, the basic trapezoid rule for approximating the integral on the area a to b of f of x dx is based on an estimation of the area beneath the curve over the interval ab using a trapezoid. The function of integration, f of x, is taken to be a straight line between f of a and f of b. The numerical integration formula is of the form the integral from a to b of f of x dx is equal to capital A of f of a plus capital B f of b. A and b are going to be selected so that the resulting approximation formula will correctly integrate any linear function. It suffices to integrate exactly two functions, 1 and x, because a polynomial of at most degree 1 is a linear combination of these two monomials. This process is called the method of undetermined coefficients. So, the basic trapezoid rule, we let a be 0 and b equals minus 1 to make things easier on ourselves. And we find the formula of this type for the integral 0 to 1 f of x dx, a of f of 0 and b f of 1. So we need to fulfill f of x is equal to 1, that's the integral from 0 to 1 dx, that's equal to 1, and that's equal to a plus b. And the integral f of x equal x, that's the integral from 0 to 1 of x dx, and that's equal to 1/2, which is equal to b. So the solution to this system of equations is a equals b equals 1/2, and from there we get the integration formula. The integral from 0 to 1 f of x dx is approximately 1/2 f of 0 plus f of 1. And by a linear mapping of y equal b minus ax plus a from 0, 1 to 8b, that's again the straight line between those 2 points, we get the basic trapezoid rule. The integral from a to b of f of x dx is approximately 1/2 b minus a times f of a plus f of b. And this is depicted over on the figure on the right. So this leads us to the basic Simpson's rule, which is we take two subintervals, a to a plus b over 2 and a plus b over 2 to b. Now what we want to do is approximate the integral from a to b of f of x dx by taking the function of integration to be the quadratic polynomial passing through 3 points, namely f of a plus b over 2, and f of b. And we want to look at a numerical integration formula of the following form, where it's equal to capital A f of a plus b f of a plus b over 2 plus capital C of f of b. The function f is going to be assumed to be continuous on the interval ab. Coefficients capital A, b, and c will be chosen such that the formula above will give the correct values for the integral whenever f is a quadratic polynomial. Now, because this is quadratic form, it suffices to integrate correctly the three functions, 1, x, and x squared, because the polynomial of at most degree 2 is a linear combination of these three monomials. So, again, we simplify our calculations going from a equal minus 1 to b equal 1, and we'll need to fulfill three equations. The integral from minus 1 to 1 of dx is equal to 2, and that's equal to a plus b plus c. The integral from minus 1 to 1 of x dx is equal to 0 when you run it out, and that's equal to minus a plus c. And the integral f of x equals x squared from minus 1 to 1 is equal to 2/3, which is equal to a plus c. Now, from that system of equations, we can solve that a is equal to 1/3, c is equal to 1/3, and b is equal to 4/3. Along with the mapping y equals 1/2 b minus ax plus 1/2 a plus b from minus 1, 1 to ab, and obtain the basic Simpson's rule, which is listed in the bottom. The top graph here shows the Simpson's rule by itself. You can again see that the resulting curve is more smooth than the trapezoid rule. And down here we see the both the trapezoid and the basic Simpson's rule compared to one another. Let's take a look at an example of how we would use this. So we want to find the approximate values of the integral from 0 to 1 of e to the minus x squared dx using the basic trapezoid rule and basic Simpson's rule. And you'll recall this is one of those ugly integrals that we looked at before that's in some ways closely related to the error function. So for solution, we let a equal 0, that's the lower bound, b equal 1, that's the upper bound. And then from the trapezoid rule, we get the following. It's approximately equal to 0.5 times 1 plus 0.3678, that's e to the minus 1, and we get a result of 0.68394. That's correct to only one significant digit, but again, it's better than nothing. Now let's see how Simpson's rule does it. And again, here we're just going to basically apply Simpson's rule without going through the derivation, and it's approximately equal to 1/6 times e raised to 0 plus 4 times e to the minus 0.25 plus e to the minus 1. And when we work it out, we get 0.7472, which is actually correct to 3 digits. And you'll recall from previous sections that the actual value in section 5.1 was computed to be 0.74682. And this function is related to the error function. You may not recall that precisely, but that's the actual value. And so we get a pretty good approximation just using this basic Simpson's rule. We're now going to look at the basic Simpson's rule with uniform spacing. So, a numerical integration rule over two equal subintervals with partition points a plus h, and a plus 2h equals b is a widely used basic Simpson's rule. And we can write it in a couple different forms. One, this form, and we can also write it in this form. This form goes from a to a plus 2h. This form goes from a to b. And so that's where we get the b minus a over 6 times f of a plus 4f times a, or 4 times f of a plus b over 2 plus f of b. And the error term for this is going to be minus 1/90th h to the 5th fourth derivative of f evaluated at xi for some xi in AB. So Simpson's rule computes exactly the integral of an interpolating quadratic polynomial over an interval length 2h using 3 points, namely the two endpoints and the middle points. If you'd like to see the entire derivation of this rule, you can find it on page 230 of the text. Now let's look at the composite Simpson's rule. Suppose that the interval AB is subdivided into an even number of intervals, say n, each of which h equals b minus a divided by n. Then the partition points x sub I equals a plus I times h, for I ranging between 0 and n, where n is divisible by 2, gives us the following. And applying the basic Simpson's rule leads to the composite version. Now, this will give you something to memorize for the test. But in all seriousness, the error term here is minus 1/80th b minus a times h to the fourth derivative of x of xi, so this one is actually o of h to the fourth. A lot of this depends on the function being well behaved, because we need a fourth derivative. In particular, many formulas for numerical integration have error estimates that involve derivatives of the functions being integrated, like this one does. An important point that is frequently overlooked is that error estimates depend on the function having these derivatives. So, if you have a piecewise function, say a step function that's being integrated, numerical integration should be broken up over the region to coincide with regions of smoothness for the function. You don't want to attempt to integrate at those discontinuities, even though some of these numerical formulas will give you nonsense if you attempt to do it. You do want to break it up so that you're integrating over these regions of smoothness. Another important point is that no polynomial ever becomes infinite in the finite plane, so any integration that uses polynomials to approximate the integrand will fail to give good estimates without extra work at integrable singularities, and those are points where you have difficulty, so you have to integrate around them, but that's a lecture for another time. So let's take a look at adaptive scheme for Simpson's rule. now we're going to develop an adaptive scheme based on Simpson's rule for obtaining a numerical approximation to the integral from a to b f of x dx. In this algorithm, the partitioning of the interval ab is not selected beforehand, but it's automatically determined. Partition is generated adaptively, so that more and smaller subintervals are used in some parts, and fewer and larger subintervals are used in other parts. In the adaptive process, we divide the interval AB into two subintervals, and then decide whether each of them is to be divided into more subintervals. We continue this until we get some specified accuracy obtained throughout the entire interval AB. Since the integrand f may vary in its behavior on the interval AB, we don't expect the final partitioning to be uniform, but it's going to vary in the density of the partition points. So, since this is adaptive, it's necessary to develop a test for deciding whether subintervals should continue to be divided. We're going to basically use the inequality 1/15 S2 minus S1, where S2 is the 2 Simpson's rule, S of AC plus SCB, and S1 is equal to SAB, which is the 1 Simpson's rule, and those are depicted in the bottom of the slide. If you're not getting enough math yet at this point in the class, there's a derivation of this rule on page 233. Now, if we don't satisfy that inequality, then we split the interval AB into two subintervals, AC and CB, where C is the midpoint. C is equal to A plus B divided by 2. On each of these subintervals, we again use the test with epsilon, replaced by epsilon divided by 2, so that the resulting tolerance will be over the entire interval AB. And you can see that because we keep splitting and splitting, that the recursive procedure is going to handle this quite nicely. Now let's look at how to describe and code this. So basically, the interval AB is partitioned into 4 subintervals with b minus a over 4. 2 Simpson's approximations are computed by using 2 double-width subintervals and 4 single-width subintervals. H is equal to b minus a, and c is equal to a plus b over 2. Those gives us the 1 Simpson and 2 Simpson calculations. Now, according to the inequality we saw with 1/15 S2 minus S1 being less than or equal to epsilon, if the 1 Simpson, 2 Simpson agree within that 15 epsilon, the interval AB does not need to be subdivided further, and we can approximate the integral using 16 times 2 Simpson minus 1 Simpson divided by 15. If we don't get that desired accuracy, then we divide the interval AB in half. The subintervals AC and CB, where C is equal to A plus B over 2, are used in a recursive call to the adaptive Simpson procedure with a tolerance epsilon divided by 2 on each. The procedure will terminate whenever all the subintervals satisfy the inequality. Alternatively, a maximum number of allowable levels of subintervals is used as well to terminate the procedure prematurely. The recursive procedure provides a pretty elegant and simple way to keep track of which subintervals satisfy the tolerance and which need to be divided further. Let's take a look at an example here. And here you can see these subintervals that we're dividing are not equal in size. And we have a pretty nasty function here that we want to approximate. It's the integral from 0 to 5 over 4 times pi of cosine 2x divided by e to the x dx. The graph you can see over in the lower right, and it has lots of twists and turns. This is going to be ugly, but the adaptive Simpson procedure is going to use a number of different panels for the different parts of the curve. As you can see in the figure, you can see the different panels that it will actually use. And let's look at the pseudocode that can handle this monstrosity. So, for this pseudocode, procedure F needs to be written for the integrand, the function that we're going to integrate. It's the name of this first argument in the procedure, and you need to include the necessary interface statements over a function pointer or a call to that function. Other arguments are the value of the upper and lower limits, a and b, of the integral, the desired accuracy epsilon, level of the current subinterval, and the maximum level depth. The author does leave out the fact that you're going to need variables for 1 Simpson and 2 Simpson, left Simpson, right Simpson, and Simpson result. So you'll need to declare those up here where you declare the variables. By writing a driver computer program for the pseudocode and executing on a computer, the authors obtained a value of 0.208 for the nasty integral that we saw in the previous slide. Newton-Cotes quadrature formulas for approximating the integral from a to b f of x dx are obtained by approximating the functions of integration f of x with an interpolating polynomial. These rules are closed when they involve function values at the endpoints, the a and b. Otherwise, they're said to be open. Now, let's look at some of these. And these are the ones with the nice fraction. Later, we'll look at Gaussian quadrature rules, which have, quote, not nice fractions. These are the nice ones. So here a is equal to x of 0, b is x sub n, h is b minus a divided by n, and each x sub I is x0 plus I times h. The error terms have h equals b minus a over n, f sub I is equal to f of xi, and a is equal to x0. The xi is somewhere in between x0 and xn, and xn is equal to b. Now you can see these are the nice fractions, so we used these a lot of times when we were doing things by hand or with calculators back in the 50s and 60s. Later we'll see the quadrature rules, which have the not nice fractions. I'd say these are pretty ugly, but they're not the ugliest. Here's Boole's rule and the 6-point Newton-Cotes closed rule. Now, again, you can see these are not necessarily the nicest fractions. Minus 275 over 12,096 is not the most beautiful error term that one could hope for, but just enjoy the fact that these are labeled as the easy fractions. Here are a couple of the open forms. There's the midpoint rule, 2-point Newton-Cotes open rule, 3-point open rule, and again you can see the fractions are getting nastier as we go along. The 4-point and the 5-point. And again, these are the easy fractions. These were ones that could be done fairly well by hand. Again, we'll see in the next section things that can't be done very well by hand or aren't very nice to do. So, over the years, there were a lot of Newton-Cotes formulas that were derived and compiled in the handbook. And that's by Abramowitz and Stegen, 1964, and it's available online. So, rather than using high-order Newton-Cotes rules that are derived by using a single polynomial over the entire interval, it's preferable to use a composite rule based on the lower-order ones. There is also seldom any advantage to using an open rule instead of a closed rule involving the same number of nodes. Nonetheless, open rules do have applications in integrating a function with singularities at the endpoints. So those ones where you have an undefined value at an endpoint or the endpoint goes off to infinity, that's where the open rules are good because they don't evaluate that endpoint. Before the widespread use of computers, these were the most commonly used quadrature rules, since they involved fractions that were relatively easy to use in hand calculations. The Gaussian quadrature rules of the next section use fewer function evaluations with higher order error terms. The fact that they involve nodes involving irrational numbers is no longer a drawback, given that we have modern computers that can do that stuff fairly quickly. So, next time we're going to take a look at the Gaussian quadrature rules, and you'll remember that when you see all those nasty fractions that I promised you.